this video we're going to talk about adding electrical potentials. If you remember, when we add electric fields, we had to draw arrows, figure out directions, we had to add them like vectors. We had to make sure they were tip to tail, and so on. Potentials are a lot easier, okay? Electric potentials. The letter for that is V, it's voltage, are scalars. So you don't have to draw arrows. You just add the numbers. Okay, but you have to watch the signs. Okay, I am careless with my signs for a lot of things, but the one place you can't be careless with signs is with electric potentials, because being positive or negative makes a big difference. So we have an example here. We have a 2 microcoulomb charge and a -4 microcoulomb charge. We want to know the net electric potential at the origin. So for part A, the first thing we're going to do is find the potential at the origin due to, say, the -4. So we'll do V -4. Equation is KQ over R. It's like the electric field, except for it's over R instead of R squared. So we get 9 times 10 to the 9th times -4 times 10 to the -6 divided by R is the distance away, so it's 3. And that's going to give us an electric potential of minus 12,000 volts. Then we're going to get an electric potential from the other charge, the positive charge. So V from the +2 charge at the origin is going to be KQ over R, 9 times 10 to the 9th. This time it's for our +2 charge, so 2 times 10 to the -6 divided by, and the distance for that one is also 3. And that gives us a value of positive 6,000 volts. So then I can combine those two, and my V net, I just have to add them up. It's going to be -12,000 plus 6,000, which is just equal to -6,000 volts. So my net voltage is going to be negative, meaning that this -4 is dominating at the origin, and that makes sense because it's a stronger charge. Step B, it's asking for the net potential at point P. So we're going to have to figure out this R here. And I think we have a 3, 4, 5 triangle. Yeah, this side over here is 3, this side is 4. So now I know this R is going to be 5. Now the nice thing is I don't have to worry about figuring out this angle because electric potentials don't have directions. So I'm going to do V is KQ over R. All right, for the -4 charge, we'll do that one first. So it's 9 times 10 to the 9th times 4 times 10 to the -6. I have to remember to make it negative, and then divide that by 5. And that's going to give me negative 7,200 volts. Then for the +2, KQ R again, 9 times 10 to the 9th, times 2 times 10 to the -6 over 5. And that's going to give me a plus 3,600 volts. So my net for those two, again, I just add them up. It's going to be negative 7,200 plus 3,600. So the net there is equal to negative 3,600 volts. Then in part C, it says how much energy to remove an electron from point P to the origin. So for part C, we're finding energy. W equals Q delta V. We're going from point P to the origin, so I'll make a note over here. Delta V equals V at the origin minus V at P. So that's going to be negative 6,000 minus negative 3,600, which gives me negative 2,400. So then I'll get work equals, now it's electrons, so the charge is negative 1.6 times 10 to the minus 19 coulombs, times my delta V is negative 2400 volts, and that's going to give me a value of 3.84 times 10 to the minus 16 joules. Now, I'm usually careless with my signs there, so it did end up being positive work, which makes sense because the voltage is more negative at the origin, so the electron doesn't want to go there, so I have to do work to make it go there. Next page, electric potential and field for parallel plates. So if I have two parallel plates like this, let's say this one's positive down here, this one's negative up here, it's going to have a voltage difference across it. There's going to be some distance across here. If I was to draw the electric field in, remember electric fields go from positives to negatives, so I'll draw those in. And we'll label that E for electric field. Remember, the electric field is a constant between the two plates because the lines are not getting closer together or farther apart. And we can calculate the electric field by doing the voltage divided by the distance. The greater the voltage, the greater the electric field is going to be. And actually, the closer those two are together, the greater the electric field is going to be, because when the charges are closer together, there's going to be more force between them. Now, there's an example. An electron is placed between two parallel plates which are 2 centimeters apart and charged to a potential difference of 300 volts. So over here I'm going to write my givens. Okay, I have an electron, so I know somewhere we're probably going to use Q as 1.6 times 10 to the minus 19 coulombs. We have a distance of 2 centimeters. We should convert that to meters, and we get 0.02 meters. And we also have that delta V is 300 volts. And how much energy is required to move the electron from the positive to the negative plate? So step 1, energy is, we find work, Q delta V, so 1.6 times 10 to 19 coulombs times 300 volts. And that's going to give you 4.8 times 10 to the minus 17 joules. Step 2, we want to find the electric field. This new equation, electric field is voltage over distance. So the voltage was 300 volts over 0.2 meters. And that's going to give me, actually a mistake, it's 0.02 meters, not 0.2. And that gives me 15,000. Now we could write volts per meter for electric field, which actually is an acceptable unit. But if you remember, we also have to use Newton per coulomb. So either one of those is okay. Next, step 3, force. F equals EQ. This is why it makes sense to use Newton per coulomb here. I'm going to get 15,000 newtons per coulomb per E times the charge is 1.6 times 10 to the minus 19 coulombs. And that's going to give me a value of 2.4 times 10 to the minus 15 newtons. Now, I didn't put directions on here, maybe I should. So the electric field, we actually have drawn it. In this picture, it's going upward. So we'll say that the electric field is up. And then the force on the electron's negative, so it's going to be the opposite direction. So it's going to be down. We could also guess that looking at this, if I put an electron here, it's going to be repelled from those negatives, subtracted the positives, so it is going to go down.